So, hello everyone, welcome back to our third day of the MoSaiQ school. I'm very happy that we have Jérôme here from CERN. He will speak about his clock developments in Paris. So the floor is yours, Jérôme.
Thank you very much, Thomas. Thank you for the invitation. So it's a pleasure for me to be there to speak in front of students and former students also. So I will try to give kind of general talks about optical lattice clocks that we focus on several aspects, but the most important one is the quantum metrology. So we are at the stage where we can start to apply quantum entanglements to sensing devices such as optical lattice clocks. So I want to show the first steps will be in this direction. So this is the outline of my talk. So I will give first a general introduction about atomic clocks. So maybe many of you are familiar, but there's no point repeating stuff that are known. Then I will show some current status of our optical lattice clocks at CERN in terms of frequency stability and accuracy. And really, a hot topic currently in the time and frequency community is the redefinition of the SI-second that is currently based on the cesium. But as you know, optical clocks are now much better than cesium, so we are thinking about how and when to redefine the second with optical clocks. And then I will really enter the topic of application of lattice clocks and quantum effects in these clocks. So let's start with atomic clocks. So just a generic slide, just to point out that here, unlike many talks that you had here, I'm talking about passive atomic clocks. So it's really a clock that is made of two components. The first one is a local oscillator, which is typically a microscopic oscillator on which an electromagnetic wave is locked. And then we lock this local oscillator on an atomic resonance, so to the value. So there are really two numbers that characterize a good clock. So the first one is the frequency stability. So it is represents the noise that we have on the frequency of the local oscillator when it's locked on the atomic resonance. And the accuracy quantifies any possible deviation between the frequency of the local oscillator and the natural frequency of the competition. And so the accuracy is defined by the uncertainty on the evaluation of the systematic effects. Okay, and of course, we're using atoms for different reasons. So the first one is that the atoms are the universal references. All the atoms in the universe of a given species are exactly identical. So in that sense, atoms are really different from, for instance, the local oscillator, which is an artifact whose frequency depends on the people who built this artifact. And of course, the second property of atoms is that thanks to laser cooling, they can be isolated from the environment and so suffer less from perturbing effects. So this is a brief history of the accuracy of atomic clocks as a function of time. So since the beginning of atomic clocks in the 50s and 70s and 60s, so the microwave clocks here in green have improved by orders of magnitude. So the latest development of these clocks are the atomic front-end clocks that is shown here, using either cesium or rubidium. And the local oscillator used for these clocks is a quartz, a maser, or a cryogenic sapphire oscillator for the best performances. And now moving to optical clocks. So currently, the local oscillator for these clocks are trustable cavities, and the atomic part is an optical transition in the electronic structure of subatoms. So a quantity that I will use later in this talk is the stability of the clock, so sigma y of tau, which represents the statistical uncertainty after integration time tau. And here, this is the formula for the ultimate stability of a clock that is limited by the quantum projection noise. So it comes from the very quantum nature of the atoms. And it's expressed as a function of the quality factor of the resonance, the square root of the number of atoms that are probed, and the square root of the number of samples that you perform, which is the ratio between the integration time and the cycle time of the clock. Now, of course, if we want to improve this stability, there are several numbers we can play with. So the first one is we have a large number of atoms, but it comes as a counterpart because when you have a large number of atoms, you have collisions between the atoms, so systematic effect associated with that. It's possible to play on the cycle time, so to have a short cycle time, to have a high rate of measurements, and also on the quality factor of the resonance. So it's the point of going to optical clocks, to have a large quality factor. So some example for some numbers from this control projection noise. So for cesium Fontaine clocks, the frequency stability, so the statistical uncertainty after 1 second of integration, is in the low 10 to the minus 14. So this is what is achieved, for instance, with cesium Fontaine at ZIRT. And somehow it's becoming a problem because this stability is achieved with a cryogenic sapphire oscillator, and as you know now, it's a bit difficult to put hand on the helium to make them work. So another example are ion clocks. So for ion clock, stability at 1 second is 1 order of magnitude higher. So why is that? It's because it's an optical clock, so the quality factor is let's say 10 to the 4 higher than microwave clocks and cesium clocks. But on the other hand, the number of atoms is much lower, so just 1 atom or a few atoms for ion clocks compared to the 6 for cesium clocks. So that's why going from cesium clocks to optical ion clocks means only 1 order of magnitude of stability. And here comes the lattice clocks. The lattice clocks are optical clocks, a large quality factor, but at the same time with a large number of atoms, the order of 10 to the 4. And so this gives the stability limited by the control projection noise that would be below 10 to the minus 17. So people are getting close to this, but are still not yet there. So there are still some technical noise that limit the stability of the clock. So far for the stability, what about the accuracy? So this is the accuracy budget of a cesium clock, so the FO2 cesium clock at ZIRT. And this is a list of systematic effects that perturb the clock transition, the frequency of the clock transition. And here in the last column, this is the uncertainty with which we can determine all these perturbations. And currently, the accuracy of these clocks is in the low 10 to the 16. And they are limited mainly by effects that are proportional to the frequency. So that's many effects that are due to the movement of the atoms. And so you see that for this effect in red, because they are proportional to the frequency, it doesn't really help to go to optical frequencies, to go to large frequencies, because the effect would just scale with the frequency. And so that's why in optical clocks, the atoms or the ions are trapped to get rid of these effects. So now I will describe more in detail the optical lattice clocks, especially the one we developed at Paris Observatory. So these optical lattice clocks consist in a set of cooled atoms. So they are first loaded in a magneto-optical trap, and then transferred in an optical lattice that is formed by a standing wave in an optical cavity. So once the atoms are trapped in this lattice, we get rid of the systematic effect associated with the motion, and so we are safe to probe the clock transition with an ultra-stable laser. So this is the probability associated with the clock transition as a function of the tuning between the clock laser and the atomic transition. So you can say that we can reach very narrow transition on the order of 1 Hz or even lower, which corresponds to a factor of 10 to the 14. Okay, and once we can see this resonance, then we can lock the clock laser on narrow resonance and then obtain the clock signal. So these optical lattice clocks, they will combine several advantages. So the first one, high quality factor because they are optical clocks, and at the same time, we have a large number of atoms. It's possible to prove at the same time 10 to the 4 atoms. So ultimately, a very good stability. So because we are tightly confined in optical lattice, so we get rid of the motional effect by being the so-called Lambda regime. So this is illustrated by this spectrum. So here, this is the transition probability associated with the absorption of the clock laser light at the front of the tuning. But you can see here we scan not only a few hertz, but over almost 1 megahertz. So here we see the carrier. So it's really the same curve as the one that was shown here. But now, on each part of each side of the carrier, we can see 2 sidebands, which correspond to the motional sidebands associated with the trapping of the atoms. And this envelope here of this curve is with the Doppler effect. So here, this would be the resonance we would have if we don't trap the atoms, but because we trap the atoms, we get rid of the Doppler effect, and the motional effects only sum up to these two motional sidebands. And because these two sidebands are resolved from the carrier, then we are not affected anymore by motional effects. And of course, the key ingredient for this clock is really the magic wavelengths concept. So, as you can anticipate, trapping the atoms in an optical lattice changes a lot the frequency of the clock transition. So, this is a light shift that is applied to the clock transition, and it is on the order of 1 megahertz. So 1 megahertz out of 10 to the 14 hertz is really not a good performance, but fortunately for a specific wavelength of the optical lattice, then the polarizability of the ground and the cyclic state are exactly identical, and so the net effect of the clock transition is. Okay, so this was a general introduction to optical lattice clocks. So this is kind of an overview of what we're doing in the optical frequency metrology group at l'ENSI at Observatoire de Paris. So this is a laboratory that is conveniently placed almost in the center of Paris, in the Paris Observatory that was built 350 years ago. And the advantage that at that time this was a countryside, so that we have a lot of real estate, even though Paris just expanded around the observatory. And so in the basement of the observatory, we have a set of experiments about optical frequency metrology. So we have two Sensor optical lattice clocks. So we will describe them a bit later. We have a Mercury optical lattice clock. The main advantage of Mercury is that its polarizability is much lower, so it's less sensitive to external perturbation. So in particular, it has low sensitivity to the black body radiation. We are starting a transportable clock with ytterbium atoms in collaboration with the Geophysics Institute in France. The main target of this clock is to have application, to demonstrate application in geodesy. And beside the clocks, we have supporting technologies. So it's a short list, but it's really a large effort to do that. So we have retractable lasers to stabilize the clock laser. We have also a project about laser stabilization on rare earth ions in the crystalline matrix, which is called spectral hole burning. And this project hopefully will give performances for the clock laser much better than cavities, and also it has many applications. And we also develop frequency comps. So with the aim of comparing optical clocks, but also to generate microwave. Now the research on frequency comp in the laboratory has somehow shrunk, and now we are moving to have operational frequency comps to support the optical clocks. And a large activity also we have is about optical fiber links. So it's good to develop optical clocks, but it's even better to compare them with clocks developed in other laboratories. And so we are in the process of building optical fiber links throughout France and connected to our European partners. And these links have the property of being phase stabilized, because you can imagine that if you transmit an ultra-stable signal throughout this fiber, the perturbation of the fiber will just degrade the stability of the signal. So it's important to take care to cancel these perturbations. So we have postdoc position available on all these topics. So if you are interested, we are looking for bright students like you. So just don't hesitate to contact us. Okay, so here are the Strontium clocks we have at CIRT. So we have two clocks that are neatly called Strontium 1 and Strontium 2. And this is the atomic level of strontium that are of interest for us. So the main transition here in the blue is to laser cool the strontium, and then the transition to the ground state and the first metal stable state is with the narrow clock transition. So these are the accuracy and stability that we reach now with these clocks. So as for the stability, when we compare the two clocks, we have a statistical uncertainty of 10 to the minus 15 at 1 second. So it means that at least one of the clock is better than 7 to the minus 16 at 1 second. And then the frequency difference between the clocks averages down with time. And when we integrate for several hours, we can reach a statistical uncertainty of 10 to the minus 17. And this is the current accuracy of the clock. So we have a number of systematic effects that perturb the clock transition. And when you sum them up, you end up with a systematic uncertainty in the low 10 to the minus 70. And these two clocks, Strontium 1 and Strontium 2, are interconnected with other clocks through the frequency cones, for instance, for the Mercury and the microwave clocks. So you can see that in this accuracy budget, the main part here is the black body radiation. So it comes from the environment of the atom that emit black body radiation. And this black body radiation, so the polarizability of the atom, induce a frequency shift. And this uncertainty comes from our uncertainty in the knowledge of the temperature of the environment, from which we have uncertainty of the amount of radiation that reaches the atoms. That's why we are currently building another clock that has a better thermal design. So here at the center, you have the trapping area of the clock that is both small and made out of copper to have low thermal gradients over the chamber, and all the heat source around the vacuum system are highly decoupled to avoid that it transmit their heat to the vacuum system. This vacuum system will be enclosed in the primary vacuum to avoid convection in the system. Okay, so first application of optical clocks is really the path to redefinition of the SI second. And the point really is to replace the SI second that is currently defined with cesium with optical transitions. And so this is the text of a roadmap. So things we have to do before this redefinition can happen. So it was set in this paper a few years ago and been working on now. And the first point is really to have good clocks. So to have clocks that are 2 orders of magnitude better than cesium. So this is mostly done, but the point of using optical clocks to define the SI second is not only to have good clocks, is to be sure that we have good clocks. And so there are 4 other points that must be fulfilled in order that we are able to redefine the SI second. And it's mainly about comparing clocks. So being able to compare remote clocks with transportable clocks, fiber links, or measurement of frequency ratios. We have to be able to connect to the current SI second by measurement of frequency ratio between optical clocks and cesium clocks. The clocks should be useful, meaning that they should contribute to TAI. So TAI is International Atomic Time, which is the basis for UTC, which is the legal time for all the countries in the world. And it's really important that we get confidence in the optical clocks, meaning that we are able to measure frequency ratio between different clocks, and that this measurement should be reproducible between different laboratories. So here I want to highlight some progress we have made in this roadmap, especially with fiber links and contribution to TI. So this is what the contribution to TI looks like. So TI, the acronym is in French because you know the Metrology Institute is located in France, so somehow now people are speaking both English and French. And so TI is Temps Atomique International. And calibrating TI means comparing optical clocks to a local realization of UTC, which is then compared to UTC by the PITM, so International Bureau for Wave Measurements. And this calibration must be operated over slots of 5 days. The reason for that is that these clocks are these various UTC realization are compared by satellite. Satellites are very noisy. So if you want to compare with a large precision, then you have to integrate for a long time. And so that's why you have to operate the clocks for 5 days. And so this is what we measured. So this was a measurement that we did a few years ago. So this is a measurement of the frequency of the local Lagrangian measure, which is the basis for the local UTC, with the strontium clock. So this is the frequency of the measure reference to the strontium clock. And here you see that we could measure almost continuously over extended period of 10 days or 22 days. So this is really a large effort. In the first measurement we did over 5 days, we had to babysit the clock, so we had to be there 9-10 days. It was very exhausting. So we should automate the clock, and now we can reach operation time of several weeks without being in the lab. So once we have done this calibration, so we send a report to the BIPM, so Bureau International des Poids et Mesures, and this report is integrated in the so-called circular T, so T for time. And it looks like this. So this is a list of all the clocks that contribute to TI for a given month. So here it was 2017, I think. It's 2019. And an important value is this column here. So it's D. It's how much the clock says that the local rotation of UTC was. So here's the contribution with the clock at CIRT, but over the last few years, there are many other laboratories who contributed to TI with optical clocks. So for instance, NICT and NMIJ in Japan, NIST in the US, CRIS in Korea, and in Italy. And this is a compilation of all the recent calibration over the last 20 years of clocks to TI. So if you want to have a look at this curve, you can see it in the BIPM website. And so in green here is a contribution by Cesium Fontaine, so primary frequency standards. And you can see that there is a handful of clocks. So in Russia, in CIRT, PTB, NPL, and in Italy, Switzerland, and China who contribute to TI with primary standards. And here, this is contribution with rubidium fontaines. So rubidium fontaines are also microwave fontaines, just like cesium, except that rubidium is not the primary standard, it's the secondary standard. And now the interesting part here is the top of this graph. It's a contribution by optical clocks as secondary representation of the exact second over time. So we had a few sporadic contributions 7 or 8 years ago, and now clocks are contributing more and more continuously to TI. So here we're really in the process of completing this step of the milestones to redefine this hexagon, meaning that the optical clocks are really used in applications, in metrology, in calibrating timescales. So second point in the roadmap I want to highlight is really international comparison by optical fiber links. So we have a set of fiber links that connect CIRT in Paris, PTB in Braunschweig in Germany, NPL in the UK, and now INRIM in Italy, and we are able to perform clock comparisons with these optical fiber links. And the advantage of these fiber links is that they can resolve the frequency difference of 10 to the minus 19, both in stability and accuracy, by integrating only for a few hours. So it's really much more performant than the satellite, because satellites, you can compare clocks at 10 to the minus 16 over several days. So here it's orders of magnitude better and orders of magnitude faster. And now with these fiber links throughout Europe, we are able to connect more than 10 optical clocks and 5 microwave clocks together. So it's really an important tool for time and frequency methodology. And of course, there are many challenges. So the first one is that it's many different people in many different institutes that we have to coordinate. So at a given time, we have to be all ready to perform the measurement, and the optical clock has to be at their best accuracy and stability at this given time, which is a bit more involving than having a good optical clocks at the time you want. And there are many scientific outcomes from this clock comparison by optical fiber links. And the first one, that's why I put this experiment in the roadmap for redefining the exact second, is that it's really a very good test for an optical second. It's really when we compare the clocks that you're able to show that the performances are material that they are reproducible. And I will show also a few applications, especially in fundamental physics. And finally, in this infrastructure, we have to compare clocks. So this installation of optical fiber links can really be seen as a shared infrastructure, and there are many other applications that can benefit from it. For instance, quantum key distribution networks that need some dedicated optical fiber links. Okay, so this is an example of an international comparison we performed comparing the clock in Paris with NPL, PTB, and through LPL, which is the laboratory operating the link in Paris. And this is the stability that we could measure for different optical clocks by performing a three corner hat. So the point is to have three clocks, and by pairs of stability between the clocks, you can derive the stability of a single clock, and so we are able to demonstrate the stability of all of these clocks. And you can see that after a few hours of measurement for all these clocks, we're able to enter the 10 to the minus 18 regime. And this is interesting because in this regime we are supposed to see tidal effects. So the tides just change the shape of the Earth. So they change the gravitational potential, and this translates into a change in the frequency difference between the clocks that we are not so far from resolving. So that was the stability. What about the accuracy? So we performed a large number of comparisons over the years. So we had a break during the COVID, but now we started in 2022, and we have a large number of agreements between the clocks, the low and the 17. So that's very satisfying, I would say. And also, we are now able to measure several frequency ratios between different species. But I think that it's good when things work, but it's also good when they don't work, because from time to time, we see disagreements that can be as large as 16. And when we see them, it's a pointer to some effect that we have not anticipated. And here I give two examples of them. So one is really fundamental. So this is an effect that we have seen in the Strontium clock at CIRT. At some point, for a comparison, we had limited lifetime of optical lattice to background gas, and we could show that there was a frequency shift associated with the pressure of background gas. That we can relate the frequency shift to the lifetime of the optical lattice. And also, from time to time, there is a technical effect that shows up. So, for instance, here we had a ground loop between the sequence of one of the clock and the thrustable cavity, meaning that the clock frequency would jump from time to time synchronously with the sequence. And of course, when you have another clock that has not the same sequence, then it makes a frequency shift. Okay, so I gave two examples that will lead to the redefinition of the SI second, so contribution to TI and comparison by optical fiber links. And so now the question we may ask is how the SI second will be redefined with optical transition and when. So how there are currently three options under consideration by the working group of the CCTF. So CCTF is Consultative Committee for Time and Frequencies. And so I'd like to detail a bit these options that are under consideration. And I will start with option 3. So you know that now currently the SI system of units, the units are defined by fixing the value of numerical constant. So the speed of light is fixed, the Planck constant is fixed, the Avogadro number is fixed, the Boltzmann constant is fixed. And now if we want to extend this reasoning to the second, then we will be tempted to set another fundamental constant to a given value. So for instance, we could set the electron mass, or we could set the Rydberg constants. So that would be a very beautiful system of units. We just fix the main constant of nature, and from this set of constants, we define all the units. So that would be really the spirit of what has been done so far. The problem is that the realization of time would be limited to 10 to the minus 12. That basically corresponds to our current knowledge of the Rydberg constant. And this is not so good because you know that now time is the frequency, the quantity that is the best measure. So we have uncertainty in the 10^16, even better than that. So this uncertainty is much better than any other unit. So in a sense, we have some margin. But if we use this option to be, then we would be limited to 10^12, and the uncertainty in the duration of time would start to spread in the user units, which would be even this. So, for instance, people that measure the frequency of quasars, astronomers, would be really limited by the duration of the second. This kind of option. So, a more reasonable option is to stay in the current philosophy of the SI second, which means simply replacing the cesium species with another species with an optical transition. And the problem that we have with this option is that we should decide on one transition. And you can see that there are many possible candidates for such an optical transition. So, for instance, strontium and ytterbium or clocks that are really widespread throughout the world, throughout NMIs, that would be good. But if you look in the ion community, so the ytterbium ion is very good performances. Strontium and calcium ion also declocked, and we can see that maybe in the future we'll have even better clock with nuclear clocks. So here we're really in a position where it's hard to pick up one candidate and decide that this would be the MoSaiQC. And so there is option 2 that I want to highlight, not only because I am the author of this option, would be to define the second with multiple transitions. So the point would be to set the Hertz not as the frequency of one optical transition, but as a combination of several transitions with different weights in the form of the geometric mean. So I will not elaborate on this, but the point would be to take advantage of all the different transitions that are currently under consideration, and above this, of all the knowledge of frequency ratios between all these transitions, so that when we want to compare an oscillator to the unit, then we would really take advantage of all the clocks. And in a sense, this system would be an optimal generation of what is currently done with primary frequency standard and secondary propagation of the system. So what is the timeline for the redefinition? So the most likely scenario, but it's not decided yet, would be that in 2026, so at the GPM, so General Conference for Weight and Measures, there is an agreement on which option to choose and possibly on which transition to choose. And also a definition of the final milestones that are required to define the second. And then 4 years after this, the next GPM, then the redefinition. So let me highlight a few applications of optical clocks. So here I want to show that the comparison of optical clocks have important application in fundamental physics. So this is a test of Lorentz variance that has been done by comparing the clocks in Paris, PTB, Van Dyck, and NPL London. And the key feature of this comparison is that these clocks are at different positions on Earth. And so as the Earth rotates, they have different velocities with respect to the universe. And so we are able to, with this, to check whether there is a preferred direction, non-isotropy in the universe. So a good candidate for this preferred direction is really the velocity of the Earth with respect to the cosmic background. So the cosmic background would be just used as a universal frame. And so we want to check if there is a frequency shift on the clock comparison that depends on the velocity of the clock with respect to the cosmic microwave background. And so when you expand the velocity of the clock with respect to the microwave background as the velocity of the clock with respect to the Earth plus the velocity of the Earth with respect to the cosmic background, and you expand, you end up on this equation. So we are looking to a frequency shift that is proportional to the scalar product between the differential velocity of the clocks and the velocity of the Earth. And this parameter alpha is a parameter that would be 0 if there is no violation of Lorentz invariance. So for special relativity, this parameter alpha is 0. But if you say that Lorentz invariance is wrong, then this parameter alpha would be different from 0. And this is the magnitude of the effect that we could resolve given the velocity of the clocks. So the ratio between the frequency shift and alpha would be on the order of a few 10 to the minus 10 and oscillating over the period of 1 sidereal day as the Earth is rotating in Earth. And now, because we are able to measure frequencies with a resolution on the order of 17 or better, you can see that we can resolve alpha with uncertainty on the order of 10 to the minus 8. So this is what we have done with the clock comparison data, and so we could reach this bound on alpha that is currently the best bound so far. So I don't know how much time I have left. We just skip this one. And I want to highlight another application of optical clocks, which is currently very fashionable, which is about geodesy. So you probably know that the lapse of time depends on the gravitational potential. So if a clock is lifted 1 meter in the Earth's gravitational potential, then its frequency changes by 10 to the minus 16. And this is an effect that is widely observed when you compare different clocks, because of course clocks throughout the world can have a high difference of 100 meters, so it's something that is really well resolved. But now comparing optical clocks allows to enter a new regime in this effect, because if we are able to compare clocks at 10 to the minus 18, it means that we are able to resolve 1 centimeter redshift. And this is something that cannot be measured with independent means, meaning that geophysicists are not able currently to tell us what is the geopotential with the 1 centimeter resolution. So here, comparing the clocks would be a measurement of the gravitational potential. And a key ingredient for this application is we to have transportable clocks, because the places where the gravitational potential is the most unknown or places where you have mountains, and so it's very interesting to bring clocks in these mountain areas. And so, for instance, this is an experiment that was done with the transportable clock at PTB that was put in the Alps and compared to the clock in Okay, so for the last part of my talk, I want to highlight a few experiments we did to try to exploit quantum correlations in optical lattice clocks. And so to motivate this, I want to show you what are the current noise sources that limit the frequency stability of the clocks. So the first noise source that limits the frequency stability is the detection noise. So why is that? When you probe the clock transition, then so you set the frequency of the clock laser at a given frequency, and you measure the probability that associated with the detuning of the clock laser with respect to the transition. But now, if your measurement of the clock transition is noisy, then you will only estimate the frequency of the clock laser, and when you feed back your measurement of the frequency of the clock laser, you introduce a noise. The second one is a different noise of the measurement of the transfer probability, the quantum production noise. So it's really because the quantum state of the atoms when the clock laser is at half resonance is a quantum superposition between the ground and excited state of the clock transition. And because you have this quantum superposition, then when you make the measurement, you have a random result with a significant ratio of 1 if you have 1 atom. But now, if you have n atoms, they all collapse independently, and so the noise will be 1 over square root of n. And from this significant ratio comes the frequency stability limited by the quantum production noise that I've shown you in the first slides of the presentation. And the last noise, so it's a bit more tricky, but currently the dominant one. So it's the tick effect. So it's a noise due to the clock laser. So it's a bit counterintuitive because the point of a clock is really to measure the clock laser noise and to cancel it. So why would this noise still be there in the end? The reason is that the clock cycle has not 100% duty cycle. So here this is a plot of the clock cycle. So when G the sensitivization function is 0, then we don't look at the atoms, and when it's 1, we are applying the clock laser on the atoms. And really the point is that in the clock sequence, there are times when you probe the atom with the clock laser, and time when you prepare or load the atom, and when you don't look at the atoms. And now, if you consider the clock laser noise here, that is represented around the frequency close to the repetition rate of the clock sequence, then you see that if you shine the clock laser at regular intervals, then you see only a part of the clock laser noise, and so you cannot correct completely for it. And here you really have a sampling effect, because, for instance, here, if you look at the long term the clock laser noise, and you shine the clock laser at regular intervals, you see that this high frequency noise here translates in low frequency noise in the clock signal. So this is a decay effect. It's a stroboscopic effect, meaning that you are looking at the clock laser at regular intervals, but not with 100% duty cycle. And this converts high frequency noise into low frequency noise. So the way to get rid of that is to have a clock that is able to probe the atoms all the time, so to go to duty cycle of 100%. So if this happens, you can see that you can really much better average the clock laser noise, and so this down conversion of clock laser noise is much less efficient. So as it is now for optical lattice clocks, this later noise, the decay effect, is greater than the control correction noise, and is greater than the detection noise. However, there is a lot of effort to improve the ultra-stable laser sources. So, for instance, with cryogenic cavity or spectral gold burning experiments. It's possible also to reduce the dead time in the clock by using non-destructive detection. So I will show an example just after. It's possible to reject the decay effect by performing synchronous interrogation of two different clocks, or by implementing zero dead time clocks. So because of all these developments, the decay effect is expected to become much smaller, and eventually the control correction noise will start to be the dominant source of instability for optical lattice clocks. And that's why you want to explore ways that will allow us to overcome the control correction noise. So the control correction is really the noise on the measurement of the observation probability, and so that's on this topic that we have to work. So this is a simplified schematic of the strontium levels. So here between the ground state and the first metastable state, you have the clock transition, so narrow transition, and to measure the probability of going from ground state to the excited state, we use this strong transition at 461 nanometers. That allows us to measure the number of atoms that are in the ground state, and from this you can deduce the transition probability by calculating 1 minus the number of atoms in the ground state divided by the total number of atoms you have in the first place. So the way it's done usually is by using fluorescence detection. So the idea is to send a strong laser pulse on this blue transition on the atoms. The atoms will fluoresce under the action of this laser light, and a camera would collect part of the light emitted by the photons, from which we can calculate the transition probability. And the problem with this method is that there's a low efficiency, meaning that the atoms that scatter light in the whole space, and the photodetector usually collects a small amount of it. And so there is a loss of information in what is given by the atoms. So this is what we call for the next part of the talk, destructive detection, meaning that to compensate for this loss of information, we have to apply a strong light on the atoms. And so it means that the atoms scatter a lot of photons. So N gamma is the number of atoms scattered, the number of photons scattered per atom, which is much greater than 1. It's so large that the atoms escape the trapping area and are lost. And so the idea would be to develop a new detection that would be able to collect all the information given by the atoms on the probing light. So now we use the same probing light, but now a much weaker light, and this light is sent on the atoms. And because the atoms are medium with an index of refraction, so the fact that you have atoms here changes the phase of the light after propagation through the atoms. And so the number of atoms, the probability, would be deduced from a measurement of this phase shift. So this is an experiment we did more than 10 years ago in this direction. So the idea was to send light aligned with the optical lattice and measure this phase shift. So to measure a phase shift, you need the phase reference. So the phase reference was a strong beam that was pitted with the beam that forces the atom. And from this interferometric measurement, we could measure the phase shift and then the number of atoms. And from that, the transition probability. It's a spectrum of the clock transition that we measure with this detection system. And this symmetry ratio was similar to what would be obtained with a camera, but the number of scattered photons was low enough so that we could recycle the atoms from cycle to cycle. So that's what I call the classical noticeability. But somehow the symmetry ratio can be improved by using a cavity. So now instead of having the one pass of the light to the atoms, we put a cavity around the atoms, and this cavity enhances the interaction between the light and the atoms, and so magnifies the phase signal. So now the idea is to measure the phase shift inside the cavity by observing how much the resonances of the cavity are changing by the presence of atoms inside the cavity. So the objectives of this new detection systems, non-destructive detection system, twofold. The first objective is to reach the classical non-destructivity, meaning that after the probing of the atoms, the number of scattered photons is low enough for the atoms to stay trapped, and so we can reduce the time required to load atoms in the next cycle, so we can reduce the peak effect. And the second objective is to go in the quantum regime. So meaning that here we can probe the atoms while scattering much less than one photon, in which case we would preserve the wave function of the atoms after probing. So this is what is called the QND measurement, so quantum non-evolution measurement. And with this kind of measurement, it's possible to overcome the quantum production noise. So this is the kind of measurement that has been done with microwave clocks. So here you have an example in Eugene Boz's group with rubidium atoms, in which they use this QND measurement to perform spin squeezing and then to reduce the uncertainty of the probability measurement. And this is another version of this same system that was done inside the cavity by the market charge. Okay, so now the challenges that we have for this kind of experiment with optical lattice clocks. There are three challenges. The first one is that now we are moving to an optical transition. So there are many tricks that were applicable to microwave transition that are not possible to apply now to these optical transitions. So this makes things more complicated. And there was an experiment by Alan Friedrich 2 years ago where they could actually demonstrate squeezing on an optical transition. The other challenge that we have with optical lattice clocks is that we have a moderate number of atoms. So the demonstration of squeezing with microwave clocks involves 10 to the 6 or more atoms. And with this number of atoms in optical lattice clocks, we have a strong systematic effect due to collisions. And so we have to work with a lower number of atoms. When we have lower number of atoms, it's harder to reach spin squeezing. And the last part, which should not be overlooked, is that we want to implement this kind of QND measurement on an actual clock system. So we don't want to have a dedicated experiment. We want it to work on a system that is able to be used as a clock. So this is how the detection system for QND that we have built is working. So the idea is that we have this cavity in which we send the blue light that we want to use to probe the atoms. And now if you look at the transmission of the cavity has resonances. So you see this kind of resonance pattern out of the cavity when you send the light to the cavity. With the arrows here. Okay, so now if you put atoms into the cavity, then the atoms will shift the resonance, meaning that the light reflected by the cavity will experience a phase shift that depends on the phase accumulated by the light inside the cavity, multiplied, enhanced by the finesse of the cavity. So in order to measure this phase, a good idea is to use an EOM, so phase EOM, which would create a strong carrier and a weak sideband that would be coupled in the cavity. And by beating the carrier that is fully reflected by the cavity and the probing light that goes into the cavity and experiences a phase shift, it's possible by this method to measure the phase shift. So it is the technique that is usually used to stabilize laser on cavities, the PDH scheme. But the problem with that is that there are many different reasons for which the resonance of the cavity would move. So it could move because you have atom in the cavity, but it could also move because you have fluctuations in the length of the cavity. It could also move because the frequency of the laser is moving. Okay, so your atomic signal would be somehow would vanish into these technical noises. So for this reason, we designed a system in which actually the two sidebands would be injected in the cavity. So the +2 sideband of the modulation of the EOM, the -2 sideband of the EOM would be both resonant with consecutive modes of the cavity. And then these two modes would be on each side of the atomic resonance, meaning that the atomic phase shift on one resonance would be, say, on the right, and it would be on the left for the other mode, because the refraction of the dispersion response of the atoms would be that opposite sign. And now, if you make a differential measurement, the phase of the sideband minus the phase of the sideband, you would get the atomic signal. Okay? So with it, the main feature is that the clock transition would be close to the center here, meaning that the frequency shift would have opposite sign on the two sidebands. But now, if you look at technical noises, so if you have laser frequency fluctuations or cavity length fluctuations, this fluctuation would rather move the two resonances in the same side. Okay, so you have a way to discriminate the atoms and the technical noise. And because of this system, we are able to demonstrate a detection that is completely immune to technical noises. So this is how it looks like in practice. So this is a scheme of the setup I've just sketched before. So here you have the optical cavity in which we inject two different sidebands, so +2 and -2 sidebands on two consecutive modes. And in the same cavity, we have the optical lattice in which the atoms are trapped. And then we have an electronic system that is able to modulate the light and demodulate to acquire the atomic signal, so the phase shift being used by the atom of the light. And there are several key features of this detection system. So the first one is that the cavity here has a high finesse for the probing light at 461 nanometers. And it means that we are able to increase the symmetry ratio by a factor of square root of the finesse, which is about 100 here in this case. And another key feature of this system is that we have a homogeneous atom cavity coupling. So the reason for that is that here these two sidebands that we get to the cavity are tuned in two consecutive modes of the cavity, and so they form each a lattice.
but you see that one sideband has one more side for the lattice. So here at the center of the cavity, the two sidebands have opposite, the intensity of the two sidebands have opposite phase, and so the blue power here at the center of the cavity is homogeneous. And it's really important because the pitch of the lattice for trapping the atoms at 830 nanometers is not the same as the one for the detection. So if you add only one sideband, you would have a lattice and you would probe the atoms in homogeneous. Okay, so this is what the results look like. So this is a typical clock sequence. So here without clock laser, so we load the atoms, we cool the atoms, and when we detect the atoms, and so the detection, the plot that I show here shows the atomic phase shift inside the cavity, starting here when we start the detection pulse. So there are several features. So here at t equals 0, you can see that there is a sharp increase in the atomic signal. It's because the blue light enters the cavity, and we have a digital system that is able to quickly lock the laser on the cavity. Okay, then we have, I'm running out of time, so I will skip that. But after some time, we are able to resolve the atomic signal and to fit it with what we expect is the way the atoms absorb photons and get hit by the photons and then escape out of the optical lattice. So here we are able to look at the noise in the detection system, and we can check really that this noise here is limited by the shot noise because the PSD of this noise is proportional to the optical power. And the number that characterizes the detection is how big is this noise, and this noise is 23 atoms. So we are able to resolve 23 atoms divided by the square root of number of photons that each atoms scatter. And it's really interesting because the noise, when you are in by the shot noise, the noise of the detection only depends on the number of scattered photons per atom and not any other parameter. And with this detection, we're able to demonstrate three different regimes. So first, the destructive regime. So it means that if we shine the probe for a very long time, so as it is done here in this plot, so it's destructive because here we lose all the atoms, then we will have a resolution that is much lower than one atom in the optical lattice. Now, if we stop the detection earlier, so we sample only for a very short time here in this curve, we are able to scatter less than 40 photons per atom, and when you do that, when you do so, the atoms stay in the optical lattice, so you reach a classical non-destructivity regime. And when we are in this regime, we are able to detect as little as 4 atoms in the optical lattice. And now, if we probe for even shorter, so it would correspond, you see here the total length here is a few milliseconds, but if you probe for a few nanoseconds, so really 1 pixel here in the plot, then you would be able to scatter less than 1 photon per atom, and this would correspond to the noise of 23 atoms. And so, with these performances, we would be able to reach the quantum regime, meaning that we would be able to have a detection noise that is lower than the control production noise for a number of photons scattered per atom that is lower than 1. And when you take the numbers that I've mentioned before, it means that this happens as soon as you have more than 530 atoms, so the square of 23, and a probe time that is shorter than 25 nanoseconds. That was kind of a challenge because the probe time is really short, especially compared to the dynamics of the cavity. And so we are blocked by this very short time. And that's why we recently built an enhanced version of this detection system in which we will work with a dual EOM system and work at various tunings, so several gigahertz, 6 gigahertz, by targeting not 2 consecutive modes of the cavity, but the next modes. And with this system, we could measure once more the atomic signal, so the phase shift as a function of time, but now scattering less than 0.1 photon per microsecond. Okay, so now we are in a regime where we can do the quantum regime for a probe time that is on the order of microseconds, which is doable with the cavity system. So next step that we are going to observe quantum correlation between consecutive pulses that are the measure of Q&E measurements. So let me give you some outlook in what we want to do next. So we have activities in metrology. So we want to develop a new clock system to reach an accuracy 10^18 or below. And also at the same time, continuing the metrological application, especially by contributing to TI. But we want to put forward these activities around quantum technologies. And as soon as we can perform QND measurements, we want to implement a screening protocol that we have published recently this year in collaboration with ICFO in Barcelona, which aims at integrating the QND measurement inside a rapid interrogation of the atoms. And this paper, it will show that we can improve already the clock instability. And one important thing when doing so is really to be able to evaluate the accuracy of the clock, in the sense that the probing light should not induce a frequency shift that would deteriorate the accuracy. So thank you very much. I will stop here and answer your questions.
Was more about this increase of PPR, because you mentioned that you designed something to increase your PPR. Can you elaborate more about it?
Yes. So actually, currently the intensity of the PPR is on the order of 10^17. It corresponds to an uncertainty on the temperature of the environment that is on the order of a fraction of Kelvin, so 0.1 Kelvin. And this uncertainty is mainly limited by the heat load around the vacuum system. So we have coils to implement the trap, and these coils produce some temperature production in the vacuum system. And so here the direction we are pursuing is to be able to have a better homogeneity. So with the system that I've shown, we expect to have an homogeneity of a few tens of millikelvins. And so that we are able to reduce by 1 order of magnitude the uncertainty of the vacuum. So this is one strategy. Another strategy, as it's followed by several groups in the world, is to use a cryogenic environment for the clock. So it's two different paths, but I really like this passive way because it's easier to operate, and so it's more compatible with operational measurements with the clock, such as computation.
This is the box, or?
Yes, so the system itself is a small vacuum system under high vacuum, and this small system is put in a larger box that could be under primary vacuum.
What is the level of this primary vacuum?
This will be just a millibar, just to avoid convection.
So this primary vacuum is interesting. So you say it's to avoid convection that disturbs the needs for the lattice.
No, because when you're not in a vacuum, the coils for the trap the heat, and then the transfer some heat to the system by convection.
The coils are still in this primary vacuum, so they need to be water cooled.
Yes. So it's at least they also have this certain vacuum system, but somehow the two systems are in the high vacuum. It makes things a bit more complicated because the plugging rate in the vacuum is smaller, and also you have to take care that the outer environment is small. You just put inner vacuum and vacuum and keep no vacuum.
So you mentioned that the filing is so what is the worst that can happen?
So the point is that when the light goes through an optical fiber, there is an index of refraction of the optical fiber, and this index of refraction can vary with time. It can vary because of vibrations, it can vary because of thermal fluctuations. The data, the and so it means that if you send light to the fiber, then the phase at the output of the fiber is completely scrambled with respect to the phase and the makes the frequency stability and stability when you go to the fiber. And the effect is already important when the short fiber, say 1 meter, and you can understand if you have fiber at 1,000 kilometers, that effect becomes. So the solution for that is to have the light sent back and forth in the fiber. Because the light is going too fast, we assume that the perturbation of the way forward are the same as the perturbation of the light comes back to the fiber. And so when you beat what goes in the fiber and what comes back, you get 2 times the perturbation. And from this measurement, it's possible to actively cancel. So it depends. So, for instance, the link in Germany from Strasbourg to Braunschweig, it's operated in dark fibers. But somehow, the fiber is quite expensive. So they have to rent the fiber, pay high price every year for that. And so in France, we are lucky to cooperate with the network provider of the National Education Ministry, and they give us not one dark fiber, but dark channel in the fiber. So it's a range of wavelengths that is 50 Hz wide. And so we send the cross-level laser together with the internet information in the same fiber. And the issue with that is that, as I told you, we would like to go back and forth in the fiber to measure the fluctuations. And the fiber for use for the equation, you get an amplifier in the way, but this amplifier are only one way. So it means that each time you have a repeater internet connection, someone from the lab has to go there and to extract the signal, put the bidirectional amplifier, and we get it to the fiber. So there are some stations for that are now being developed commercially by the Nikos company. Okay, so the clocks and what is said in the links are not separate. So in the link, it's a beam at 1.5 micrometer that is sent. So we have dedicated the cross-level cavities at this wavelength, and this light is sent to the link. And then we want to compare clocks. We locally compare the infrared laser to the atoms, and so then we sum up different frequency difference in order to compare the clocks.
You mentioned that we have this traffic with higher logarithm modes. What is the advantages compared to 0 mode?
So one of the limitations for the accuracy of the clock is the cold collision between the atoms. So when you have a 1 lattice, so you trap the atom for 1 millimeter, and so with 1 millimeter you have 1,000 sites for trapping atoms. But if you want to trap 10,000 atoms, you have 10 atoms per site. And when the atoms start to interact, now an idea to overcome that is to use the 3 lattice. So you would have 3 directions, and so you would have many more sites. But the advantage of that is that it's harder to have a cavity maintenance with 3 lattice, because you have to do 3 cavities in 3 directions. And also for the family isotope, you have to shoot the polarization cannot be well defined in the 3 directions at the same time. So the idea would be to stick to 1 configuration, but instead of using the TM001 mode, you would use a Lagrange mode, in which you have as 8 different sites, each transverse site of the lattice. So you want to trap more atoms. So for now, we have already generated this Lagrange mode. We have injected them in the cavity, and we could show that we have enough trap depths to take out the atoms. So expect already trap to actually put the atoms.
So you mentioned so that one of the big problems at the moment is the the optical itself, and you mentioned that spectral burning would be a way out there.
So we are going to the stability of the procedure. The whole burning is using a spectral feature in ions trapped enclosed in the protein matrix. And this system is not very temperature. And the point is that when you send to stabilize laser this ensemble of ions, then you make the ensemble transparent because you have metastable device this ion at very temperature. And so the spectral feature of the crystal becomes transparent and as low as a few hundreds of watts. Okay, and we could use spectral feature, this transparency of the crystal as a frequency reference to calculate that. And one of the advantages is that many different ions in the crystal that have different environments, so they all answer at different frequencies over the Earth. And so you can burn many different holes at different frequencies inside the crystal. And it's like having many entities working in parallel.
What are some of the technical requirements of the laser that you use for non-destructive detection? Or
No. For the 461 nanometer transition, it's just a standard laser because the magnitude is 30 megahertz. So we have the laser that is a CDL, the magnitude is 21 megahertz. And that's really enough because we have this cyclone technique which allows to project the
and then the quantum structure, is that different?
yes.
So on the topic of QFD measurements, then you mentioned that you can do it in a very short time now, which is nice, because if I understand correctly, this is just the readout part, right? So the long interrogation time that you would want with your plug laser, you can still keep, right? You can keep a long frequency of that. So what about the actual recycling of the atoms themselves? Now the aim with this is that you don't keep the atoms out of the lattice, and so they stay. Most of them will be staying inside the lattice even after this detection. And then you just provide a little bit of sci-fi cooling.
Yes. So the point we are so we don't do it now because on the system we have mechanically actually the battery is not so good. Actually because the windows of the system are good, it's flexible, and over time it's flexible outcasted. And so the lifetime is to 1 second. So in 1 second, we don't have time to cycle that so much. Okay. But in principle, yes, the sequence would be to poke the atom, the clock laser, detect, and then find a second media, and then
difference between your certain time, you have certain
so the stability is exactly the same, because of the same clock laser, and the accuracy, so for the social clock, it's the measure 1.7, and for the other clock, the second one, it's equally because of this issue we have with so the lifetime is too short to have a good accuracy. So what the accuracy is 10/16, and there should be observed frequency shift in the clock. So it's the need that it's ready because of epoxy when it's time. So the first place is because by the way, we want to 17, and we want to be asked. I think we find at least they say that if you flash the epoxy fast enough, then you avoid this problem. Yeah, we have to cure the epoxy that gets harder. If you cure it fast enough, we have a piece of the point. But the point that this issue showed up for several years. So after test, and also when you flash the epoxy, you have a high quality. So now we go back to the epoxy for the system.
So I would thank you again very much, Jérôme.